Chapter 3: Ion Channels as Targets of Psychopharmacological Drug Action. Many important psychopharmacological drugs target ion channels. Ligand-gated ion channels as targets of psychopharmacological drug action. Membranes are decorated with all sorts of ion channels. The most important ion channels in psychopharmacology regulate calcium, sodium, chloride, and potassium. There are two major classes of ion channels. One class of ion channels is opened by neurotransmitters and goes by the names such as ligand-gated ion channels, inotropic receptors, or ion channel link receptors. The other major class of ion channel is opened by the charge or voltage across the membrane and is thus called a voltage sensitive or voltage gated ion channel. Ion channels are opened and closed by actions of neurotransmitter ligands at receptors acting as gatekeepers. When a neurotransmitter binds, it causes a conformational change in the receptor that opens the ion channel. Thus, a neurotransmitter, drug, or hormone that binds to a receptor is sometimes also called a ligand, which literally means tying. Numerous drugs not only immediately alter the flow of ions through these channels, but with a delay can also change the downstream events that result from transduction of the signal that begins at these receptors. And these include changes in gene expression and thus changes in which proteins are being synthesized and many other functions. Now these functions can range from synaptogenesis, receptor and enzyme synthesis, and downstream communication. About a fifth of psychotropic drugs currently utilized in clinical practice, including many drugs for the treatment of anxiety and insomnia such as the benzodiazepines, are known to act at these receptors. Also, drugs that act on these receptors can have an almost immediate effect. This is in direct contrast to the action of many drugs that act at G-protein linked receptors, some of which have clinical effects such as antidepressant actions that may occur with a delay because it requires initiation of changes in cellular function activated through the signal transduction cascade. Ligand-gated ion channels, their structure and function. These are actually a type of receptor and they also form an ion channel and comprises of several long strings of amino acids assembled as subunits around an ion channel. And they also have multiple binding sites for everything like neurotransmitters, ions, and drugs. At these sites, some ions can travel through the channels, whereas others can bind to the channel itself. Multiple neurotransmitters and co-transmitters can act at separate binding sites at the same time. And allosteric modulators, which can be natural substance or drugs that bind to the site different than where the neurotransmitter binds to increase or decrease the sensitivity of channel opening. Pentameric subtypes. These are assembled from 5 protein subunits, hence the name. Each subunits have 4 transmembrane regions. The receptor sites are in various locations on each of the subunits. Some binding sites are in the channel itself. This pentameric structure is typical for GABA, nicotine, serotonin, and glycine receptors. The subtypes of these pentameric receptors are defined based upon which form of each of the 5 subunits are chosen for assembly. Although the natural neurotransmitter binds to every subtype of inotropic receptor, some drugs are able to bind selectively to one or more of these subtypes, but not to others. Tetrameric subtypes. The inotropic glutamate receptors comprise subunits that have 3 full transmembrane regions and a 4th reentrant loop. This tetrameric structure is typical of the inotropic glutamate receptors known as AMPA and NMDA. This chapter also has the agonist spectrum, so let's revise it once more. As discussed previously, an agonist changes the conformation of the receptor to open the ion channel to the maximum amount and frequency allowed by the binding site. Now, an ion channel can open to even a greater extent, that is, more frequently than with a full agonist alone. But this requires the help of a second receptor site, that of a positive allosteric modulator or PAM. As we previously studied, antagonists stabilize the receptor in the resting state, which is the same as the state of the receptor in the absence of agonist. There is essentially no difference between the presence and absence of an antagonist, and therefore the antagonist is said to be neutral or silent. Now, the resting state is not a fully closed ion channel, so there is some degree of ion flow through the channel even in the absence of an agonist or even in the presence of an antagonist. And this is called the constitutive activity. Antagonists of ion channel link receptors reverses the action of agonists and bring the receptor conformation back to the resting baseline state, but do not block any constitutive activity. Now, a partial agonist produces a change in the receptor conformation such that the ion channel opens to a greater extent and more frequently than it is in its resting state, but less than in the presence of a full agonist. On the other extreme, the inverse agonist produces a conformational change in these receptors that first closes the channel and then stabilizes it in this inactive form. This inactive conformation produces a functional reduction in ion flow and in consequence the signal transduction compared to the resting state. In many ways, therefore, an inverse agonist does the opposite of an agonist. Now let's discuss different states of ligand-gated ion channels. There are even more states of ligand-gated ion channels than those determined by the agonist spectrum. This range from the maximal opening of the ion channels caused by a full agonist to the maximal closing of the ion channel that is caused by an inverse agonist. Desensitization is yet another state of the ligand-gated ion channel caused by prolonged exposure to agonists, and may be a way of the receptors to protect themselves from overstimulation. The continuous presence of the agonist over time leads to another conformational change where the receptor essentially stops responding to the agonist. This can at first be reversed relatively quickly by removal of the agonist. However, if the agonist stays much longer, on the order of hours, then the receptor converts from a state of simple desensitization to one of inactivation. This state does not reverse simply upon the removal of the agonist. It takes hours in the absence of agonist to revert to the resting state. This is best characterized for nicotinic cholinergic receptors. These ligand-gated ion channels are normally responsive to the endogenous neurotransmitter acetylcholine, which is quickly hydrolyzed by an abundance of the enzyme acetylcholinesterase. But the drug nicotine is not hydrolyzed by the acetylcholinesterase and is famous for stimulating the nicotinic cholinergic receptors. Thus, these receptors require hours in the absence of the agonist to get back to the resting state. Now let's discuss allosteric modulation, PAMS and NAMS. These are other molecules that are not neurotransmitters but can bind to the receptor or ion channel complex at a different site from where the neurotransmitter binds. These sites are called allosteric sites, literally meaning the other site, and ligands that bind there are called allosteric modulators. Interestingly, they have little or no activity on their own in the absence of the neurotransmitter. And as can be expected, there are two forms of allosteric modulators: those that boost what the neurotransmitter does and are thus called positive allosteric modulators or PAMS, and others that block what the neurotransmitter does and are thus called negative allosteric modulators or NAMS. Now, PAMS causes conformational changes in the ligand-gated ion channel that open the channel even further and more frequently than happens with a full agonist by itself. Good examples of PAMS are benzodiazepines. These ligands boost the action of GABA at GABA A type of ligand-gated chloride ion channels. Thus, in the presence of benzodiazepines, the GABA binding to GABA A sites increases chloride ion flux, and thus increasing the effect of GABA by opening the ion channel to a greater degree or more frequently. And clinically, this is exhibited as anxiolytic, hypnotic, anticonvulsant, amnestic, and muscle relaxant actions. Now, example of a NAM is benzodiazepine inverse agonist, and they can appear as net agonist or net antagonist depending upon the amount of naturally occurring full agonist neurotransmitter that is present. These diminish the chloride conductance through the ion channel so much that they can cause panic attacks, seizures, and some improvement in memory. That is the opposite clinical effects of a benzodiazepine. Thus, the same allosteric site can have either NAM or PAM actions depending upon whether the ligand is a full agonist or an inverse agonist. NAMs for NMDA receptors include phencyclidine or PCP, also called angel dust, and its structurally related anesthetic agent ketamine. Now let's discuss voltage sensitive ion channels, their structure and function. Critical aspects of nerve conduction, action potentials, and neurotransmitter release are all mediated by another class of ion channels known as voltage sensitive or voltage gated, and they are regulated by ionic charge or voltage potential across the membrane in which they reside. Now, as we know, the action potential is triggered by summation of various neurochemical and electrical events. The first phase is sodium rushing downhill into the sodium deficient negatively charged internal milia of the neuron, when voltage sensitive sodium channels open the gates. Now, a few milliseconds later, the calcium channels also get the same idea, with their voltage gated ion channels opened by the change in voltage potential caused by the sodium rushing in. And finally, after the action potential is gone, during recovery of the neuron's baseline internal electric milia, potassium makes its way back into the cell through potassium channels while sodium is again pumped out. As expected, several psychotropic drugs work on these voltage sensitive sodium channels and voltage sensitive calcium channels. Now let's discuss voltage sensitive sodium channels in detail. Now these are similar to the voltage sensitive calcium channels, as both have a pore, that is the channel itself, allowing ions to travel through them. But these voltage gated ion channels have a more complicated structure. These channels are long strings of amino acids comprising of subunits, and 4 of these different subunits are connected to form a critical pore known as an alpha subunit. In addition to these, other proteins are also associated with the 4 subunits. The subunit of a pore forming protein has 6 transmembrane segments. Of these, segment 4 can detect the difference in charge across the membrane and is thus the most electrically sensitive part and functions like a voltmeter. It can thus alert the rest of the protein and begin conformational changes of the ion channel. Now each subunit of a voltage sensitive ion channel has an extracellular amino acid loop between transmembrane segments 5 and 6. This serves as an ionic filter and is located in a position so that it can cover the outside opening of the pore, and thus allowing only sodium ions to filter through the sodium channel and only calcium ions to filter through the calcium channels. Now 4 copies of the sodium channel version of this protein are strung together to form one complete ion channel pore of a voltage sensitive sodium channel. And the cytoplasmic loops of these amino acids that tie the 4 subunits together are sites that regulate various functions of the sodium channel. Interestingly, the loop between the 3rd and 4th subunit of the sodium channel, there are amino acids that act as a plug to close the channel on the inner membrane surface of the pore. Now understandably, the sodium is kept out of the neuron when the channel is closed or inactivated, and the direction of sodium flow is into the neuron when the channel is open. These channels may have one or more regulatory proteins, some of which are called beta units. These are located in the transmembrane area and flank the alpha pore forming unit. They may modify the actions of the alpha unit and thereby indirectly influence the opening and closing of the channel. These alpha and beta units may be phosphoproteins themselves, with the possibility that their own phosphorylation state could be regulated by signal transduction cascades and thus increase or decrease the sensitivity. Both these subunits may have various sites where various psychotropic drugs may act, especially anticonvulsants, some of which are also useful as mood stabilizers or as treatment for chronic pain. There are three different states of these sodium channels. The first one is the channel can be open and active. And when a sodium channel needs to stop ion flow, it has two states that can do this. One state acts very quickly. It flips the pore inactivator into place, stopping ion flow so fast that the channel has not yet even closed. And the another state of inactivation actually closes the channel with conformational changes in the channel's shape itself. Now there can be many subtypes of these sodium channels. As previously stated, these channels may be the site of action of several anticonvulsants, some of which have mood stabilizing and pain reducing properties. Now let's discuss voltage sensitive calcium channels. These also have subunits with 6 transmembrane segments, with the segment 4 acting as a voltmeter and with the extracellular amino acids connecting segments 5 and 6 acting as the ionic filter. Calcium channels also string together 4 of their subunits to form a pore, in this case called an alpha 1 unit. There is no pore inactivator working as a plug for the calcium channels as was described above for the sodium channels. Instead, the amino acids connecting the 2 and 3 subunits work as a snare to hook up the synaptic vesicles and regulate the release of neurotransmitter. In all cases, the direction of ion flow is from outside of the cell to the inside when the channel is open. Now several proteins flank the alpha pore, forming unit of the calcium channels called the gamma, beta and alpha 2 delta, in which the delta part is transmembrane and alpha 2 part is extracellular. The alpha 2 delta protein is target to many psychotropic drugs such as anticonvulsants, pregabalin and gabapentin. These are also involved in regulating the conformational changes of the ion channel to change the way the ion channel opens and closes. Now as expected, there are several subtypes of calcium channels as well. Calcium channels that are associated with ligand-gated ion channels are members of an entirely different class of ion channels. The subtypes of calcium channels of most interest to psychopharmacology are those that are presynaptic and thus regulate neurotransmitter release and that are targeted by certain psychotropic drugs. Another interesting subtype is the L channel. These channels exist not only in the central nervous system but also on vascular smooth muscles, where they regulate the blood pressure and where a group of drugs known as the dihydroxypyridines, also known as the calcium channel blockers, acts. Two other channels known as the R and the T channels are also of interest as some anticonvulsants and psychotropic drugs interact there. Now the presynaptic N and PQ channels are linked by molecular snares to the synaptic vesicles. Some experts think of this as a cocked gun loaded with neurotransmitter packed in a synaptic vesicle bullet. Now if a drug interferes with the ability of the channel to open and let in calcium, neurotransmission can thus be prevented, which actually may be desirable in states of excessive neurotransmission such as pain, seizures, mania and anxiety. When a nerve impulse invades the presynaptic area, this causes the charge across the membrane to change, in turn opening the calcium channels. This allows calcium to enter and makes the synaptic vesicle dock into and then merge with the presynaptic membrane, spilling the neurotransmitter. Anticonvulsants are thought to act on various sodium channels as well as calcium channels. Now let's discuss ion channels and neurotransmission. The initiation of chemical neurotransmission is by a neuron's ability to integrate all of its inputs and then encode them into an action potential. The nerve impulse is then sent along the axon via voltage-sensitive sodium channels. The action potential could be described as lighting a fuse. The burning edge of the fuse is carried out by a sequence of sodium channels. These open in a sequence, allowing the sodium to pass into the neurons and then carrying the electrical impulse along. When this impulse reaches the axon terminal, it meets the calcium channels in the presynaptic neuronal membrane, which are already loaded with synaptic vesicles and ready to fire. It opens the calcium channels, allowing calcium to enter and the neurotransmitter to be released. As the impulse arrives in the axon terminal, it first hits the sodium channels. Now positive sodium charges are detected by the sodium channels voltmeter. This then opens the last of the sodium channels, allowing sodium to enter. This then changes the electrical charge near the calcium channels, which is in turn is detected by the calcium channels voltmeter. Next, the calcium channel opens. Chemical neurotransmission has now been irreversibly triggered, and the translation of electrical message into chemical message has begun. This causes the synaptic vesicles to dock into the insides of the presynaptic membranes and merge with it, finally spilling the neurotransmitter contents out of the membrane and into the synapse.